Welcome to the class. Today we're going to have a look at the second lesson in chapter 8. We're going to talk about two topics. First, magnetic force on moving charges, and next, magnetic force on a current carrying conductor. Okay, each second, the cyclotron particles accelerator at the Trump National Laboratory in Vancouver, which is shown in figure 1, accelerates trillions of protons to speeds of 224,000 kilometers per second. At this speed, a proton traveling in a straight line would reach the moon in less than 2 seconds. The magnetic force of a series of large electromagnets directs a proton in the cyclotron along a spiral path with an increasing radius. These powerful magnets produce a magnetic field over 10,000 times as strong as Earth's magnetic field. The unit of magnetic field strength in the SI system is the Tesla, which is denoted by uppercase T. A Tesla is defined in terms of other SI units by this convention, which means 1 Tesla equals 1 kilogram per coulomb second. The magnetic field close to a refrigerator magnet has a magnitude of about 0.001 Tesla. The magnetic field strength near Earth's surface is approximately 50 mu Tesla. An MRI unit, MRI unit can have a magnetic field strength of 7 Tesla. We can observe a magnetic field exerting a force on moving charges using a cathode ray tube and a magnet, which is shown here in figure 2a, where a beam of electrons move across the cathode ray tube. Bring in a magnet near the cathode ray tube, which is shown here in figure 2b, shows how a magnetic force deflects the electron beam. Okay, so let's have a look at a charge in a magnetic field. The 18th century French scientist Ambray demonstrated that two current-carrying parallel wires could be made to attract or repel one another depending on the direction of the current in each wire. He also showed that a magnetic field could be made to force a current-carrying conductor to move. Ambray's discovery applies to more than just electrons flowing in a wire. Magnetic forces act on all types of electric charges, such as electrons, protons, and ions. An important property of the magnetic force is that it depends on the velocity of the charge. The magnetic force is non-zero only if a charge is in motion. This property of magnetic force is not shared by the gravitational force and the electric force. Those forces are both independent of velocity. So here, figure 3 shows a particle with positive charge Q moving with velocity vector v. The direction of vector v is south. The magnetic field, which is denoted by uppercase vector b, points east. And the magnetic force on the charge is acting vertically upward. Given a magnetic field B and the charge Q moving with velocity v, the magnetic force exerted by B on Q is given by this formula. Fm equals QV cross B. In other words, Fm equals QVB sine theta, where theta is the angle between V and B, right? This is according to the definition of cross product. in figure 3, apparently theta is 90 degrees, right? So in this case, theta 1 is equal to 1. So note here, the magnetic force, just like any other force, is a vector quantity. Notice that the equation provides only the magnitude of the magnetic force. Next, here, figure 4 shows how we can also determine the direction of the force using the right-hand rule for a moving charge in a magnetic field. So here, this only gives the magnitude of the magnetic force, MV, Fm. Okay, so next, let's have a look at how we can determine the direction of the magnetic force. Okay, so as shown here in figure 4, we can determine the direction of the force using the right-hand rule for a moving charge in a magnetic field, which states that if you point your right thumb in the direction of the velocity of the charge, or vector v, and your straight fingers in the direction of the magnetic field, which is uppercase vector v, then your palm will point in the direction of the resulting magnetic force, which is Fm. You can use the right-hand rule to determine the direction of the magnetic force on a moving charged particle, okay? So if Q is greater than 0, the force will be along positive z-axis. Otherwise, if Q is less than 0, the force will be along the negative z-axis. So applying the right-hand rule to figure 3, the direction of the magnetic force, so this is figure 3. If you apply the right-hand rule, the direction of the magnetic force is vertically upward along the z-axis, positive z-axis, right? Using the right-hand rule gives the direction of the force when Q is positive in the equation for the magnetic force. The magnetic force is up for a positive charge with V and B directed as shown here in figure 4. The force for a negative charge, such as an electron, is down. Okay, I'll give you some time to have a look at the right-hand rule here. Any questions, just let me know, okay? Okay, actually, there are two hand rules you can use. You can choose either one you like. We have just talked about the first one, which is shown here in figure B, right? The rule we just learned is illustrated here in figure B. So if you point your fingers in the direction of the magnetic force, magnetic. So if you point your fingers in the direction of the magnetic field with the velocity coming out of your thumb, then the magnetic force on the positive particle is in the direction you would push with your palm. And then the magnetic force on a negative particle is opposite, right? Well, the second method is also applicable, which is shown here in figure A. So you can choose either one you like. Okay, the second type of right-hand rule states that if you point your fingers in the direction of the velocity v and then curl them toward the direction of the magnetic field b, then your upright thumb shows the direction of the magnetic force on the positive particle, right? Because according to definition, the magnetic force equals, well, actually, this is a vector. The vector magnetic force Fm equals QV cross B, right? So according to the definition of V cross B, we can use the right-hand rule to determine the resultant force, F. We have already studied this in the vector class in mathematics, right? So in this way, you can determine the resultant force Fb given the direction of V and magnetic field B, right? Also note that theta should be between 0 degrees and 180 degrees. Okay, so you can choose either one you like. One, you want to determine the direction of the resultant magnetic force given V and B, okay? Well, the magnetic force has several distinct characteristics. One already mentioned is that Fm depends on velocity, right? Another characteristics different from gravitational and electrical forces is that direction of Fm is always perpendicular to both the magnetic field and the particle's velocity. The direction in which the force acts and the direction of the field are always parallel for electric and gravitational field. Okay, next let's have a look at a tutorial in which we'll calculate the magnitude of a magnetic force and use the right-hand rule to determine the direction of the force. Okay, so let's consider all right, so let's consider tutorial 1, calculating the magnetic force on moving charges here. So this tutorial shows how to calculate the magnetic force for a negative charge and for a positive charge, and determine the direction of deflection of a charge by Earth's magnetic field. So let's consider sample problem 1. Here in figure 5, the electron moves at a speed of 54 meters per second through a magnetic force with a strength of 1.2 Tesla. The angle between the electron's velocity vector and magnetic field is 90 degrees. Assume a value for the electron's charge of Q equals negative E, which is negative 1.60 times 10 to the power of negative 19 coulombs. So there are 4 questions you need to answer. First, what is the magnitude of the magnetic force on the electrons? Express the answer in newtons using 1 Tesla equals 1 kilogram per coulomb second. B. Use the right-hand rule to determine the direction of the magnetic force. C. Calculate the gravitational force on the electron. The mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. And last, what is the ratio of the gravitational force on the electron to the magnetic force on the electron? Okay, here I'll give you 10 minutes to think about this question by yourself. Then we'll have a look at the solution together, okay? All right, have you finished? Let's have a look at the solution together. Okay, question A, we know the magnitude of the electron's charge is 1.60 times 10 to the power of -19 coulombs, and speed is 54 meters per second, and magnitude of the magnetic field is 1.2 teslas, and theta, which is the angle between the velocity of the magnetic field, is 90 degrees, right? So according to the formula, the magnitude of the magnetic force, Fm, equals QVB sine theta. We can find the magnitude of the magnetic force, which is 1.037 times 10 to the power of -17 newtons. Then we can use a right-hand rule for a positive charge to determine the direction of the magnetic force. So for a positive charge, we can point the fingers of right hand in the direction of the magnetic field, then point thumb in the direction of the velocity of the particle. The palm points in the direction of the magnetic force for a positive charge. In this case, though, the magnetic force for a positive charge points into the page, but we know the magnetic force for an electron, which has a negative electric charge, right, should be in the opposite direction of the magnetic force for a positive charge, and should be pointing out of the page. As to the question C, we know the mass for the electron is given to be 9.11 times 10 to the power of -31 kilograms, right? So the gravitational force on the electron is MEG. Put all the values in, we know the magnitude of the gravitational force is 8.928 times 10 to the power of -30 newtons. Okay, so in the last question, we know the magnitudes for both the magnetic force and the gravitational force. Then the ratio between the gravitational force and magnetic force is 8.6 times 10 to the power of -13. That's the ratio of gravitational force to the magnetic force on the electron. Any questions? No? Okay. Then let's have a look at another problem. So here we have a proton just moving along the x-axis at a speed of 78 meters per second. It enters a magnetic field of strength 2.7 teslas. The angle between the proton's velocity vector and the magnetic field is 38 degrees, which is shown here in figure 6. Also, the mass of the proton is given to be 1.67 times 10 to the power of -27 kilograms. So there are two questions you need to answer. First, calculate the initial magnitude and direction of the magnetic force on the proton. Then determine the proton's initial acceleration. Okay, I'll give you 5 minutes to have a look at this question, and then we'll have a look at the solution together. Okay. All right, let's have a look at the solution together. So in question 1, we know the magnitude of the magnetic force is QEB sine theta, right? So put all the values in, we can find the magnitude of the magnetic force directly, which is 2.075 times 10 to the power of negative 17 newtons. Then to decide the direction of the magnetic field, note that, the direction of the magnetic force, note that the magnetic force should be perpendicular to both the velocity and the magnetic field, right? So it's either pointing into the page or out of the page. And note that there are two methods, two types of right-hand rule we can use to determine the direction of the magnetic force. You can choose either one. So for example, if we use the first one, we can point the fingers of the right hand in the direction of the magnetic field and direct your thumb along the velocity vector of the proton. Then your palm is facing in the direction of the magnetic force, which is out of the page. And also note that this particle has positive charge, so the magnetic force should be pointing out of the page. Okay, in question B, the acceleration is Fm over m, right? We already know the magnitude of the magnetic force, and also we know the mass of the proton. So we can find the magnitude of the acceleration, which is 1.2 times 10 to the power of 10 meters per square second. Okay, do you have any questions? All right, if no questions, let's have a look at another problem here. During a thunderstorm, positive charge accumulates near the top of a cloud, and negative charge accumulates near the bottom of a cloud, which is shown here in figure 7. When the charge built up is strong enough, negative charge moves rapidly from the cloud to the ground as lightning strike. Assume the charge velocity vector is perpendicular to the ground, and Earth's magnetic field is horizontal, directed north. Can you determine the direction of the deflection of this charge by Earth's magnetic field? Okay, I'll give you 3 minutes to have a quick look at this question, and then we'll have a look at the solution together. Okay, any ideas? Well, actually, assume we have a positive charge here, and if we have a positive charge moving downwards, let's have a look at the magnetic force for positive charge first. So according to the right-hand rule, we can point our fingers of right hand in the direction of the velocity of the positive charge from the cloud towards the ground, right? Then point our fingers in the direction of the magnetic field, which is north. Then our palm should point in the direction of the resulting magnetic force out of the page, right? But here we are considering the negative charge. Therefore, for a negative charge, the magnetic field should be in the opposite direction, which is pointing into the page, right? So if a negative charge coming downwards from the cloud to the ground, the magnetic force exerted on it should be pointing into the page, which is to the direction of west. Okay. So we can make the final statement. When lightning strikes, Earth's magnetic field deflects the negative charge towards the west. Okay, do you have any questions? All right, if no questions, that's the first half of today's lesson. Let's take a 10 minutes break, and after that, we'll have a look at the second part of this lesson. Okay, welcome back to the class. Next, let's have a look at the second part of today's lesson. We're going to have a look at magnetic force on a current carrying conductor. Other than the musicians, probably the most important parts of a concert are the speakers. You might have seen the large boxes that transmit sounds to both performers and the audience, which is shown here in figure 1. Speakers are so common that we rarely think about the impact this invention has had on our culture. People use speakers at music concerts, in cars, and in portable devices. Telephones, computers, and televisions all rely on speakers to transmit sound. Intercom systems in buildings, megaphones used by firefighters and police officers, and even electronic readers for sight-impaired people are all possible because of the speaker. So how does a speaker work? Inside the speaker is an electromagnet as well as a permanent magnet. The magnetic field of the permanent magnet exerts a force on the current in the coil of the electromagnet. The speaker uses force to produce sound waves. Simply put, a speaker works because a current-carrying conductor experiences a force in a magnetic field. So let's have a look at the magnetic force and current. An electric current consists of a collection of moving charges. We can therefore use a formula for the magnetic force on a single moving charge to determine the magnetic force on a current-carrying wire. This force is important in many applications, including electric motors. Consider a current-carrying wire placed in an external magnetic field as shown here in figure 2. The magnetic field, which is denoted by vector B, is uniform and perpendicular to the wire. An external force, not the current in the wire, produces this field. We can calculate the magnetic force on the wire due to this external field by adding the magnetic force on all the moving charges in the wire. So a segment of the wire of length L is shown here in figure 3. The current, which is usually denoted by uppercase I, in this segment is I equals Q over delta T, where Q is the electric charge that passes by one end of the wire segment in the time interval delta T. This equation is the relationship between charge and current we have studied before. The magnetic force on this moving charge is given by Fm equals QVB sine theta. That's the magnitude of the magnetic force, right? And we also know the speed of the charge is just V equals L over delta T. So substituting the speed V in the magnetic force equation gives us Fm equals QVB sine theta, which is QL over delta T times B sine theta, or Q over delta T times LB sine theta. Using the relationship between the current and the charge, I equals Q over delta T, we can get the magnetic force on the current carrying conductor is Fm equals ILB sine theta, which is shown here in this formula. Okay, this gives the magnitude of the magnetic force, which is ILB sine theta. The magnetic force on the moving charge is really force on the wire. So we can rewrite the equation to express this relationship explicitly. F on wire equals ILB times sine theta, where theta represents the angle between I and the magnetic field B. So here, figure 4 shows how to use the right-hand rule to determine the direction of F on wire. Begin with your fingers of your right hand in the direction of the magnetic field and point your thumb in the direction of the current. Then your palm points in the direction of the force on the wire. The external magnetic field pulls this wire downward as long as the current is directed to the right. The magnetic force on the current is due to the force on the moving charge. So the right-hand rule used here is similar to the other right-hand rules we have just used before, right? The direction of the current replaces the direction of the velocity v for a moving charge. Okay, do you have any questions? So note here, the right-hand rule also applies for the current carrying conductor. Okay. All right, if no questions, let's have a look at a sample problem in which we'll calculate the magnetic force on a current carrying wire in a magnetic field. So here, consider a piece of wire which is 45.2 centimeter long, has a current of 12 amperes, which is shown here in figure 5. The wire moves through a uniform magnetic field with a strength of 0.30 Tesla. Can you calculate the magnitude of the magnetic force on the wire when the angle between the magnetic field and the wire is A, 0 degrees, B, 45 degrees, and C, 90 degrees? Okay, I'll give you 5 minutes to have a look at this question by yourself, and then we'll have a look at the solution together. All right, now let's have a look at the solution here. So note that we can use the equation for the magnitude of the magnetic force on a current carrying wire. F on wire equals ILB sine theta, right? Also note that 1 ampere equals 1 coulomb per second. So put all the values in, we have the magnetic field on the wire, magnetic force on the wire equals 1.627 newtons sine theta. So for question A, when theta equals 0, we know F1 on wire equals 0 newtons. Then in question B, when theta equals 45 degrees, then sine theta equals approximately 0.707. In this case, the magnetic force on the wire is approximately 1.2 newtons. And in the third case, when theta equals 90 degrees, we know the magnetic force on the wire is approximately 1.6 newtons. So the magnitude of the force on the wire is 0 newtons when theta equals 0 degrees, 1.2 newtons when theta equals 45 degrees, and 1.6 newtons when theta equals 90 degrees. Have you got this correctly? Any questions? Okay, if no questions, let's have a look at another problem. Oh, here in this scenario, two electrical poles support a current carrying wire. The mass of a 2.5 meter segment of the wire is 0.44 kilograms. A 15 ampere current travels through the wire. The conventional current is oriented due east, horizontal to Earth's surface. The strength of Earth's magnetic field at the location is 57 mu Tesla and is oriented due north, horizontal to Earth's surface, which is shown here in figure 6. So can you determine the magnitude and the direction of the magnetic force on that 2.5 meter segment of wire? Then calculate the gravitational force on the 2.5 meter segment of wire. Okay, again, I'll give you 5 minutes to have a look at this question, and then we'll talk about the solutions together. Okay, you can start now. Okay, now let's have a look at the solution to this problem. So we are given the following information. The magnitude of the magnetic field is 57 mu t, which is 5.7 times 10 to the negative 5 Tesla. And the current is 15 ampere. And L is 2.5 meters. And theta is 90 degrees, right? So we can use equation the magnetic force on wire, F on wire equals ILB sine theta to determine the magnitude of the magnetic force. Then use the right-hand rule for current carrying wire in a magnetic field to determine the direction. So if we put all the values in, we know the magnetic force on the wire is approximately 2.1 times 10 to negative 3 newtons. Then using the right hand rule, point the fingers of your right hand in the direction of the current, which is east. Next, curl or fingers in the direction of the magnetic field, north. Then our thumb should point in the direction of the resulting magnetic force, which is upward. So we can make the final statement like this. The magnitude of the magnetic force on the 2.5 meter segment of wire is 2.1 times 10 to the power of negative 3 newtons. The force is directed upward, right? Any questions? Okay, so for the second question, this is more straightforward, right? So the gravitational force exerted on the wire is just mg. So put the mass and the gravitational constant in the formula. We can find the gravitational force on the 2.5 meter segment of wire is approximately 4.3 newtons. Okay, have a look at this question here. Do you have any questions to ask? Okay, if no questions, let's have a look at the loudspeakers we have just mentioned at the beginning of the second half of this lesson. So figure 8 here shows how a loudspeaker uses magnetic force on the current to produce sound. The wire coil inside the speaker is part of the electromagnet. Electrical signals corresponding to sounds produce a changing current in the coil. The changing current produces a changing magnetic field around the coil. The permanent magnet also has a magnetic field. This field exerts a force on the current carrying wire. Variations in the current produce variations in the force on the wire in the coil. The coil moves back and forth in response. The vibrating coil causes the cone to vibrate, pushing sound waves through the air and into your ears. So this is a mechanism a loudspeaker works. Next, let's have a look at the electromagnetic pumps. An understanding of the magnetic force on a current enabled medical researchers to devise electromagnetic pumps to move fluids in kidneys and artificial hearts. Traditional mechanical pumps can cause damage to blood cells. The use of magnetic fields eliminates this problem. Scientists are able to keep blood flowing to the heart during kidney dialysis. For example, by creating a magnetic field over tubes of blood containing an electric current. A magnetic force acting on the charged particles can keep the blood in motion. So these are the applications of electrical forces or electric field. Okay, so that's the end of today's lesson. I'll see you next time. Bye.